All right, hello class. I am back again to talk about aerodynamics. Again, we've already gone over this in class, but I'm just getting these video lectures up here so you guys have something to go off of and review. So I had success finally in uploading the first portion of aerodynamics. I'm going to try to make this one a little shorter because that one is going on an hour, 45 minutes. But again, I love teaching this kind of stuff, and I love finding these relationships between these different forces and just kind of understanding what's happening when we do certain things or when certain things happen in the aircraft. So we're going to talk about the things outside of those primary four forces we talked about before. Remember the lift, the thrust, the weight, and the drag. We're going to talk about the additional forces we subject the aircraft to in turns. We're going to talk about adverse yaw, which comes from turning. Overbanking tendency, which is something we need to deal with, and then climbs and descents. I'm going to talk a lot more about climbs because energy management is essential to flying and climbing especially. So we'll kind of break that down as a whole, but let's get started with turns. So when we talk about aircraft turns, like what makes the turn actually happen? And some people you ask might say, oh, if we move the control yoke in the direction of the turn, we should turn. So that says that the ailerons are what cause the aircraft to turn. And some people say, well, you need to yaw the aircraft in the appropriate direction for the turn to happen. So then we'll have to use the rudder, right? So it's not really either of those things. It is a combination of those things, but the force that really makes the aircraft turn through use of both of those control surfaces is the horizontal component of lift. So up until now, we've been viewing lift as a purely vertical force, right? We kind of talked about induced drag and how that bends it backwards a little bit. But from that, we have a little component of drag. But for the most part, we've been thinking about lift in a vertical direction, right? And the way we've always viewed lift is kind of off the side of the airplane, right? We've always had that side profile view, right? But now we have to kind of change that so that we're looking at the front or the back of the aircraft, right, along that longitudinal axis. So we do still have lift acting upward, and we now refer to this because there are multiple directions that this lift can act. We now refer to this as the vertical component of lift when we are talking about lift in a turn. And of course, the lift that acts in the direction of the turn is horizontal component of lift. How can this be lift if it acts in the direction of the turn? Well, it just is, right? So when we bank ourselves into the turn, think about how the direction of the wings change, right? We no longer have both of those wing tips, I guess, on a horizontal plane, right? And that's parallel to the horizon anymore, right? We've got one wing that's above the other, right? So if lift is generated via that disparity in pressure, right? The high pressure on the bottom, the low pressure on top, just because we've changed the orientation of the wings a little bit doesn't mean that relationship still isn't there, or that it isn't there, right? It's still there. It just now acts in a different direction. So lift altogether acts in sort of a diagonal direction, and this is what we call total lift. Okay, so total lift acts in a diagonal direction. So if I draw what I'm talking about here, so I'll get my pen. So if we're not in a turn, if we're straight and level, this is what the wings look like, right? And where'd my wings go? There we go. Okay, and the lift acts like this, right? Because it is perpendicular to that surface, right? That's creating the lift. But if we enter a turn, we've got the wings looking like this, and then here's our aircraft body. And overall, the lift still acts in that same direction, right? But again, anytime we have anytime we have a diagonal force or vector or anything like that, then we have to break it up into pieces. So this is vertical lift right here. That's the vertical component. And then the lift that acts in this direction is the horizontal component of lift. So both together create total lift. Okay, hopefully that makes sense with the drawing. Now, if we think about the relationship between the two, if our total lift remains the same, right, when we are straight and level, and then when we enter a turn, then if that force is the same, the only thing that changes is the amount of vertical component there is and the amount of horizontal component there is, right? But if we add up those two, right, the summation is still the same amount of lift. So if we are increasing the horizontal component of lift, yet maintaining the same amount of total lift, then that vertical component decreases, okay? If we roll out of the turn, we are decreasing the amount of horizontal component of lift that the aircraft is creating and increasing the amount of vertical component of lift that the aircraft is creating, right? But we're still maintaining the same amount of lift. Now, where this gets to be a problem is if we are rolling into a turn, right, and we're increasing the horizontal component of lift, and that vertical component of lift is decreasing, if we don't do anything to supplement the lift or create more lift, more total lift to make up for that loss in vertical component, then we will descend, right? So we have enough horizontal component to maintain our bank or rate of turn, right? Horizontal component is directly related to rate and bank of, I guess more so bank, right, of turn. So if we have a 60-degree bank, we're going to have far more horizontal component than a 15-degree bank, right? But if we do nothing to make up for that loss in vertical component of lift, then we will lose altitude, right? Because we have to have enough lift acting vertically to maintain our position, right? Our altitude. So we probably don't think so much about it anymore after our first few flights, but it becomes a force of habit, right? Anytime we enter a turn, we know we're going to lose out on that vertical component, so we add back pressure to counter that, right? To adjust for that, so we don't lose altitude. Okay. So again, right, for the I guess no, not the last time because we'll probably cover it again, but another time, right, for Newton's third law to pop up and be used as an explanation for something. So when we break down these forces, right, we have that vertical component, we have the total lift, we have the horizontal component of lift. Anytime we create a force in any direction, right, there is a opposing force in an opposite direction. So in the case of vertical component of lift, right, we're very familiar with the fact that that is weight that acts in the opposite direction, right? If lift acts upward, weight acts straight down. But when we get to the total lift and the vertical component, those are kind of some new things to talk about. So let's talk about horizontal component first. Um, if we have horizontal component of lift acting in direction of the turn, then a force acting and equal and opposite force acting in that opposite direction is going to be what we call centrifugal force. We just kind of give it a name, right? But really it's inertia. Think about if you make a turn to the right, then your body kind of has that equal opposite reaction to the left, right? And that's inertia. We don't really talk about that in the terms of centrifugal force. I think mainly we talk about it as centrifugal force because we are making a turn, right? So we've got that rounded path of travel. And there would always be inertia present if we made a 360-degree turn in our car, right? But because we're turning 90 degrees and the turn stops, it goes away. So I think that's why we view this more so as centrifugal force. It's an outward force that's always present as long as you are turning. Yeah, so that's just kind of a fancy name for inertia. And then when we talk about total lift, the force that counters that is going to be resultant load. So if total lift is a combination of vertical component of lift and horizontal component of lift, then we can assume that resultant load is a combination of the counter forces, right? So a combination of weight and centrifugal force or inertia creates that resultant load, okay? So again, as we talked about before, right, if we want to have a high enough vertical component of lift to maintain our altitude, then we need to add enough back pressure to supplement that. So we are increasing the total amount of lift to keep that vertical component where it needs to be. And then as a result, right, our weight is not going to change unless we start throwing stuff overboard. But that relationship will be equalized between that vertical component of lift and weight. But because we've added that horizontal component of lift, right, then our centrifugal force is going to be stronger, right, and then the resultant load is going to be strong as well, right, enough to counter that total lift. Okay, so here's a better representation of that relationship, you can see that everything is equal in this particular diagram. So if we didn't add enough back pressure, what would happen when we entered this turn would be that our vertical component of lift would be somewhere down here. But this right here, this segment exists because we are adding back pressure. Right, I'm not going to try to write the whole thing. That was really sloppy. But because we are adding that back pressure, right, that supplements our vertical component of lift so that it can be equivalent in size and magnitude to our weight, so that we won't descend. Okay, and then that keeps our vertical component at the same place. Remember, we're splitting up this total lift into two parts. So whatever our bank angle is controls the horizontal component of lift, and then the fact that we added enough back pressure to not descend keeps our vertical component of lift straight and strong, and then we create this much total lift, and then that's opposed by all these other forces we've talked about. So actually this diagram is a good transition to discussion on resultant load and load factor. So resultant load, remember, is just that combination between centrifugal force and weight. That's kind of the overall force. But you can see here in the diagram, right, that weight is blue and total lift is blue. And why that is because that creates something that's different from resultant load that people tend to conflate with resultant load, called load factor. When we talk about load factor, it is literally a ratio between that total lift and weight, right? And when we consider load factor, the way that we treat it is as a multiplier, right? So load factor is a measurement of how many units of gravity there are that are imposed on the airplane. So if we are in unaccelerated flight, then that means we have a ratio of 1 to 1, right? So if we were in unaccelerated flight, then this total lift value would be the same size as this weight value down here. But you can see that's obviously not the case, right? So if we're comparing the amount of total lift we have to the amount of weight we have, this would be definitely a ratio of something like maybe, I don't know, 1.5 to 1, right? So if we divide the 1.5 by 1, we get 1.5. So then that would be 1.5 Gs, or units of gravity, and we would use that as a multiplier for our weight. So if our aircraft really weighs, let's say, 2,000 pounds, if we put it on a scale and it weighs 2,000 pounds, if we have a load factor of 1, that means it really does feel to the wings and the rest of the airplane like it is just 2,000 pounds. So, right, whatever the weight is times 1, so 2,000 times 1 is just 1 G. But if we take that 2,000 pound aircraft and we subject it to 1.5 Gs, and the way we get 1.5, remember, is if we have 1.5 times the total lift as we have of the weight, so a ratio of 1.5 to 1, that 2,000 pounds is now multiplied by 1.5. So it feels to the airplane like it has to support 3,000 pounds, right? You can imagine how stark this multiplier becomes as we increase that bank, right? And you can see this load factor chart on the left here. So it's pretty much 1, right? A load factor of 1 until we get to about 30 degrees of bank, right? It's probably slightly above 1 at that point because we do have that horizontal component of lift, and then we have to have more total lift overall if we want to maintain altitude. But you can see there's this just absolutely massive exponential increase as we increase our bank, right? And when an aircraft is designed, it does have a limit to how many Gs that it can take. So, for instance, I think the 172 positive G limit, I think, is positive 3.8 Gs. And you can see, right, if we follow this red line here, it looks like maybe around 75-ish degrees of bank is where we reach that limit. Right, so it's important for us to observe these limits, because if we have too much stress on that airframe, right, it's not going to be able to support itself, and those wings are going to break off, and other control surfaces are going to break off, and substantial damage leads to an unflyable aircraft. So we have to be careful. We can't be reckless with the way that we are imposing these forces on the aircraft, even when we're doing something like steep turns, right? We can't just yank back on the controls because we know that the aircraft has limits, right? So you can see here, right, if we go with that 2,000-pound aircraft example, if we subject that thing to, let's just make it simple, let's say 4 Gs, right? Then that means we are slapping a multiplier of 4 on that 2,000, right? And that also means that there are 4 times as much total lift that the aircraft has to supply to maintain altitude as weight. So 4 times whatever that weight is that it has to support, right? So the 2,000 times the 4 gives us 8,000 pounds, right? That aircraft is having to support a weight of 8,000 pounds. That's what it feels like to the aircraft. So it's not going to like that very much, right? And it's going to probably break up, right? Okay. Um, so when we talk about load factor, the other thing to consider is the fact that load factor increases our stall speed. So we're familiar with all of the published stall speed. So we have like VS and VSO and everything. All of that assumes that we are in unaccelerated flight, right? That we have 1G, 1 unit of total lift to 1 unit of weight. If we go beyond that, right, then our stall speeds increase. And you might have noticed this if your flight instructor has ever demonstrated an accelerated stall. And remember, stalling is just the fact that we've exceeded that critical angle of attack. It says nothing about our speed because we can stall that airplane at any speed. Um, the thing that we should be concerned about in terms of speed is what happens to the aircraft as a result, right? Are we stalling at a slow enough speed that the aircraft just stalls with no damage, or are we stalling at a speed that's too fast that also causes the aircraft to be damaged, right? There are some published V speeds that come from that, namely VA, right, our maneuvering speed. If we are to have a stall, right, some sort of abrupt control input that leads to a stalled state above VA, there is a good chance that we will have some structural damage happen, okay? But if we make sure to operate ourselves below VA and we have a stall below VA, then the aircraft should stall before substantial damage occurs. So that's kind of the thing in mind with VA, right? That's why VA is important. Always stay below VA when you're doing things that have abrupt maneuvers and things, right? We don't want to overstress the aircraft to the point that it breaks. Um, but when they do the accelerated stall, right, the scenario we usually use to demonstrate that is entrance into a steep turn, right? So we roll into our 45 degrees of bank, and because it is a demonstration, right, we want to make sure we are well below VA, so we slow down that aircraft to 80 knots before rolling in. So we'll roll into our 45 degrees of bank, and we'll basically just add a ton of back pressure, which is a kind of abrupt motion, right? And as soon as we hear that stall warning horn, we are adding that power and getting that nose down, right? And rolling those wings level to recover from that stalled state. We never let it go to a full stall because we don't want to, again, risk overstressing or damaging the aircraft or anything like that. And then if we weren't coordinated properly, right, that would also be disastrous because those are ingredients for a spin. But we always recover at that first indication. And what usually happens is that first indication happens to be that stall warning horn. And it usually happens somewhere in the low 70s, right? So low 70s is about 30 knots faster than our published stall speeds, right? So it is possible to stall that aircraft at any speed. You could even stall it if you were close to V&E. But again, it's a matter of substantial damage occurring along with the stall, right? So that aircraft is going to break. You're not going to really have time to observe the stall. So that's why we just keep it below VA for our safety. Okay, we don't want to overstress. Let's talk about adverse yaw. This is kind of a fun thought process to talk about as well. So adverse means opposite. So we have a yaw in the opposite direction of aileron travel, I will say. I won't exactly say turn, but a turn is the situation where we encounter adverse yaw the most. Okay, and an easy way to think about adverse yaw is the fact that it's a differential on induced drag between the wings, right? So one wing has more induced drag, the other has less. So let's just use the scenario of rolling into a turn to the right to discuss adverse yaw. When we roll into a turn to the right, we know that if we're doing a coordinated turn, right, we have to use all of our control surfaces. So ailerons, rudder, and elevator, right? We have to use all of those. And I say elevator because we need to add that back pressure to maintain that altitude. So that's how I teach my students is I ask them, are you coordinated, right? And R, the word stands for ailerons, rudders, elevators. So make sure everything is working. Keep that airplane coordinated in flight and maintain that altitude. So when we enter the turn to the right, we know that we have to turn the controls to the right. And what that does to our ailerons via cables and pulleys and linkages of that sort is that it causes that aileron on the right side to go up, right? Easy way to remember this is if you turn both your hands, if you put your thumbs up and you turn both your hands in the direction of the flight controls, then your thumbs will point to the right wing, and that's where your aileron goes up. So thumbs up, ailerons up or aileron up is a good way to remember that. So the one on the right side goes up, and the one on the left side goes down. Now, we know that the one on the right side, when it goes up, it spoils that airflow slightly, so we don't have as much lift created on that side. And then the one on the left, when it goes down, it changes the camber of the wing, increasing the angle of attack of that wing in that spot. Okay, so when that happens, more lift is generated on the left side than the right side, and that left wing ascends and the right wing descends, right? And then, of course, we need that rudder to kind of yaw ourselves into the turn, and we've got a decent looking turn going, right? Now, as we have the controls applied in those directions, right? We have to experiment, or I guess not really, but explore the induced drag, right? We know that induced drag increases anytime we increase the angle of attack. Those two things have a direct relationship. And we know that we're increasing the angle of attack on the left wing. So therefore, by rule, the induced drag on that left side must increase. If we have more induced drag on the left side compared to the right side, then the left side hangs back, right, and that right side pulls forward. But if we're trying to execute a turn to the right, um, that's not what we want to happen, right? So that's where that usage of that right rudder in the turn introduction comes into play. Now, once you are established in the turn, you depending on your degree of bank, right? You don't have to have really any aileron pressure in either direction or rudder pressure in either direction because you are established in that turn, right? So if you are in and those ailerons are neutral, you won't have adverse yaw to really fight, okay? So just remember adverse yaw is an induced drag differential. Whichever aileron goes down, that's the side that has more drag and hangs back, which is always to the outside of the turn. Well, not always, right? I should be careful there. No absolutes. We'll talk about exceptions to that in a little bit. And then if we were to turn it around the opposite direction, right? If we were doing a turn to the left, then on that initial roll-in, we would have adverse yaw acting to the right. The other thing we can do is we can kind of play with some things, right? We can combine some thought processes. So if we know that adverse yaw acts to the outside of the turn, at least initially, then think about those turning tendencies we've had to deal with. We know that most of them create a motion to the left, right? It's mostly a yawing motion to the left, okay? So if we are entering that turn to the right, which way is adverse yaw acting in? Yeah, to the left, right? So we have both left turn, or I don't want to call them left turn tendencies, but we have turning tendencies acting to the left in a yawing fashion, along with the adverse yaw, which is also a yaw to the left. So we will need more right rudder to enter that turn to keep that airplane coordinated, right? Because it really wants to move to the left. It really wants to yaw to the left. But if we change that, right? If we say we're entering a turn to the left, which way are those turning tendencies acting? Still mainly to the left, yawing motion, okay. And then we have adverse yaw acting in which direction? To the right. So in that instance, right, the turning tendencies and the adverse yaw are basically fighting one another, okay? You're still going to need a little bit of left rudder in the direction of turn to keep that adverse yaw from becoming too strong, but there's less left rudder you have to use compared to a turn to the right. So it's just kind of cool to combine these things and think about what our control inputs look like. If we put all the pieces together, what are we as pilots having to do to maintain that coordination, right? To fight these things. Where are these things working in tandem with one another, and where are they fighting against each other? right? So interesting things to explore. There are some design features that kind of limit some of these phenomena. So differential ailerons are installed for the purpose of limiting that induced drag differential, so there's less adverse yaw. And what happens is when the ailerons move, they're designed in a way that causes that aileron that deflects up to move farther than the one that deflects down. Okay, so if it moves farther out into that airflow on that side, then that increases the drag, right? It spoils that airflow over the top of the wing a little bit more. So there's a little bit more drag created, getting us closer to an equilibrium between the two. Now, it's not perfect because we still have to fight it, but you can imagine how much worse it would be if we didn't have those differential ailerons. And when you're running that pre-flight, you can actually check and see this, right? You can move the ailerons up and down, and you can see that the ones that go up, or the one that does go up, moves a little bit more than the one that goes down, right? So just try it out and see. Next thing we had to talk about is overbanking tendency. So before we talked about a disparity in induced drag, right? That's where adverse yaw comes from. Well, this is more so an airspeed differential, right? Or a rate of travel differential is another way to think about it between the wings. So if we are in a turn, right? Let's go to the right again. We know what happens to the ailerons, right? And that's all fine and dandy. We'll fight the adverse yaw with our rudder in the direction of turn, right? At least for the entry. When we are establishing the turn, we have to think about the travel of the wings, right? The distance they have to travel. So let's say this right here is a point that we're trying to turn ourselves around. In order for us to have a smaller radius of turn, we have to increase the rate of turn, right? So that means a greater bank angle, okay? So here's our little airplane. Let's see if I can kind of draw it decently. Okay, so there's a nose up front, and there's the, maybe I'll give these wings a little bit more life. Okay, man, that's the hardest part of doing these is drawing. Okay, so if we are maintaining an equal distance around this particular point, this blob I've drawn here, you can see, right, this inboard wing here has a smaller or shorter distance for travel, right? So this is the path of the inboard wing, and that has a smaller radius of turn compared to the outer wing, right? Sorry, this drawing is not exactly the best, but I'm making it work. Okay, so here's our aircraft after we get done with the turn, right? When we're like 180 degrees from where we started. So there it is, right? So this inner wing travels less, it moves less. So if we kind of think about the propeller, right? We know that the portion near the hubs doesn't have to move as far as the outer tips of the propeller blade. So the same thing is in effect here, right? The outer wing has to travel at a faster rate because it has more distance to cover than the inner wing. So if we move something a little faster through the air, what happens to the lift imposed on that object? If it's designed to create lift, like the wing is, right? It's an airfoil. That lift creates on that side, or that lift increases on that side, right? So in this particular turn, I know I said we were doing a turn to the right, so I apologize that I drew a turn to the left. But what happens here is the lift created on the right wing in this turn to the left is greater, right? It increases. And when we have that increase in lift, because of airspeed in this case, right, increase of airspeed of that wing, then that wing has a tendency to lift up more than we want it to lift up, okay? So then what happens to our bank angle is that it increases more than we would like it to. So if we were looking for 45 degrees of bank, it might cause our wing to go towards 50, 55. And how do we fix this? Well, we need to have, not rudder, aileron in the opposite direction, right, to neutralize that, that tendency, okay? Now, depending on our rate of turn or bank angle, right, they have a direct relationship. We need to we might need to have some opposite aileron or we might not. If you were doing a relatively shallow turn, then the dihedral design basically provides that sort of stability to the aircraft, right? It allows for the bank angle to be neutralized. So if you did maybe a 10-degree bank to one side or the other, the dihedral design would cause the aircraft to return to straight and level most likely. And you can see right on the wings here, you can see how they have this little dip towards the fuselage. The tips are higher than the roots, and that is the dihedral design right there. How this works is, let's say you are in a slight bank and you didn't intend to be in that bank, right? Let's say there's like a gust of wind that causes you to bank to the left. What happens is there's a slip that is created as a result, right? A slip happens anytime you do not have enough rudder input for the rate of turn, right? So if you were in level flight and you intended to continue in straight and level flight, but you've got this dip happening, that means you have no rudder input most likely. And if you are banking to the left, right, the required rudder would be some left rudder, right? But you don't have that. So you don't have enough for that rate of turn. So when you have a slip happening like that, there is essentially more airflow that is exposed on that side of the dipped wing, right? Because when you're slipping, the direction of the wind that interacts with the wings and the fuselage changes, so it's slightly more exposed to that airflow. And when that happens, right, that allows more air to interact with that surface, and the angle of attack is momentarily increased, which brings that wing back up and levels the airplane. Okay. So that's sometimes nice to have, right? Sometimes if you are intentionally trying to do a 10-degree bank or 15 or whatever, sometimes that can be annoying, right? But if we have that dihedral trying to decrease that bank, then with our control pressures, right, we're going to have no choice but to, go ailerons in the opposite direction, right? So, wait, am I getting that? No, I'm sorry. We're going to have to keep ailerons in the direction of turn, right? If we want to have a shallow bank maintained, because the aircraft is going to try to maintain or try to return us to level flight, okay? So I just kind of jumbled that up massively, but this next slide will kind of help out with that. So shallow bank, remember the dihedral is kind of that force that's winning, right? It's trying to get that airplane back into straight level. So if we want to maintain a shallow bank, and again, I don't put numbers on this because it's different for every airplane, but let's just say like 10 degrees, right? If we're trying to maintain that bank to fight the dihedral to maintain the 10, we're going to have ailerons in the direction of the turn, right, or the bank, okay, to maintain that. Once we get to the moderate bank, right, we've got, again, overbanking tendency and dihedral kind of fighting against one another. So if we were trying to maintain, I don't know, 25 degrees of bank or something like that, then we might be able to have neutral ailerons, right? And that's because the overbanking tendency of the airplane is equalized by the, or I guess, canceled out by the dihedral effect, right? They're going to be equal. So they neither will be winning. So we don't need any aileron in either direction to maintain the bank. And then if we go into a steep bank, right, I can say with certainty that if we are doing steep turns at 45, 50 degrees, then the dihedral effect is not going to be strong. The overbanking tendency effect is going to be stronger and more pronounced. So your bank angle is going to increase if you do not have opposite aileron to some degree. So get some opposite aileron in there to keep that bank angle at 45 or 50 degrees. Okay, so depending on your desired bank angle, you might have different control inputs because of that relationship between the dihedral design and the overbanking tendency. Okay, so here are a few different scenarios you might find yourself in on the regular that you can kind of think about, right? So if you're basically correcting your heading, you're going to put a very small bank in there, right? And you have to keep those controls into the turn, otherwise that airplane's going to go back to straight level. If you're doing clearing turns, you likely have a medium bank, right, or moderate bank, so you'll probably be able to just have controls neutral. And then if you're doing steep turns, you will likely have to have some sort of opposite aileron, right, to make sure that the overbanking tendency is not increasing your bank. And then we can also kind of think about the adverse yaw as well, right? So depending on where our aileron inputs are, then that would affect how much adverse yaw there is. So that's why I was careful to say earlier that it's not just at the beginning of the turn where you'll have that adverse yaw. It can happen at any stage of the turn depending on your relationship between the dihedral design and the overbanking tendency. So if we think about like shallow bank during corrective actions, we know if we're keeping the ailerons in the direction of turn, right, we're going to have adverse yaw acting in the opposite direction, which means we will also need rudder in the direction of turn. Okay. If we have a moderate bank or medium bank, right, for like maybe clearing turns, then we will have to have probably neutral ailerons. So if they're neutral, we're not going to have any what am I trying to say, adverse yaw, right? Because the ailerons are not deflected in either direction. And then if we've got a steep bank, right, then we know that we will likely have to have opposite aileron and then like opposite direction of in the opposite direction than the direction of turn. So if we have that happening, then we will have actually adverse yaw acting in the direction of the turn, right, or the bank, I should say, and we will likely have to decrease the amount of rudder we need in the direction of turn, right? So we're not going to have that much. Okay, so everything affects everything when we compare all of these things. All right, let's move on to forces and climbs. So we know that lift and thrust are those forces that help us out with that, right? We have to be moving forward to make that climb happen. We have to have enough lift to overcome weight in that moment to change our flight path to one, that elevates us. And when we talk about climbs, right, we have to assume that the angle of attack is the thing that is increased for the most part to assume another flight path, right? So remember, flight path is that direction that the airplane is moving. It doesn't really have anything to do with the pitch attitude for the most part. You can be traveling straight ahead and have a low pitch attitude or high pitch attitude, or I guess angle of attack in that case, right, would be the most congruent term to use. But when we want to change our flight path, we generally speaking have to increase that angle of attack, right? So as soon as we initiate that transition to change the direction of our flight path, we have to increase that angle of attack to some degree. And it's a momentary thing, right? Once we are established on that new flight path, right, the angle between that relative wind and angle of attack changes, right? It decreases. So think about it this way, right? We've got the chord line like this, right? If we're moving ahead, we've got relative wind moving this way, right? So here's our angle of attack before the climb. This is like straight and level. And then when we are changing our flight path, right, there's a moment where we are still on that straight flight path, but yet the angle of attack has increased, right? So we changed the AOA, okay, by increasing or changing the location of that chord line. And then once we get ourselves back on that new flight path, right, our flight path is going to look kind of diagonal in nature, right? So our relative wind is going to run parallel but opposite direction to that. But this chord line location has not changed. But because the flight path has changed, right, this angle of attack here when we are established in the climb looks more like it did when we were in straight and level flight, right? It's not as big. So we have that change that happens momentarily. And when we start that climb, right, increasing the angle of attack for that moment causes the drag to increase, right? So drag is greater than thrust for a little bit there, and that's when we decrease our airspeed. So we could have full power, but pitching the nose up like that to achieve that new flight path causes a increase in drag so that we lose airspeed. Right, once we are in that established climb, what should happen is that the thrust and drag forces should become equal again. We shouldn't lose out on any more airspeed. It should just be stationary, so pitching for our 79 or 57 or 60 knots, whatever it is, and we're in the climb, right? For most climbs, there has to be excess thrust that allows the airplane to climb. Okay, so we have to have enough power or thrust to do the climb, right? Sometimes it is power, sometimes it is thrust, and we use those terms kind of interchangeably, but they're not the same thing. If we talk about power, we're talking about the rate at which work is being done, right? If we think about work, we're talking about watts, kilowatts as a unit, but work is being done on the aircraft to climb it up, right? And the faster that rate of work is being done, the more power there is, right? And the more or the faster we will climb. Thrust is basically just a force that's measured in pounds or newtons. So it's a force imposed on an object to move it in a certain direction, right? So thrust we think about as a forward force, but if we pitch that nose up enough, change our flight path and everything, it becomes a little bit more than a forward force. We have to think about it like a vector, right? In a diagonal direction, we have to break it up into pieces. Okay, so that's thrust versus power. Depending on the type of climb we're doing, we would prefer to have excess thrust. Depending on the type of power, or I'm sorry, depending on the type of climb we're doing, we might prefer to have excess power, right? So we have to make use of the energy available to the aircraft to make the climb happen. There are two types of energy that we are concerned about when we're flying, right? The first is kinetic energy, which is basically airspeed. So the faster we're moving, the more kinetic energy we have. If we, I don't know, landed at a faster airspeed, right, and we had kind of a hard landing, we would be transferring more energy into the ground. It wouldn't go anywhere because the ground has a lot of mass, so it takes a lot to move that. And a little old airplane on the Earth doesn't have that kind of power, but that would be that transfer of kinetic energy. Okay, if you're thinking about kinetic energy in terms of that set of balls, you lift one up, drop it, and then the energy is transferred all the way to the ball at the end, and then it goes back and forth like that. Um, that's same thing, kinetic energy, right? And then we have potential energy, which is altitude, right? So the higher we are, the more potential energy we have. If we were to have a complete power loss or no wings or whatever, right, we would fall downward. We have that gravity, I guess the relationship between gravity and us creating that potential energy for our use, right? And even if we have power and wings still, right, we can still make use of that potential energy. We basically convert one of these types of energy to another type. Okay, so when we're climbing, we are sometimes trading kinetic energy for potential energy. So we might slow ourselves down in order to gain altitude, and that happens during a normal climb, right? Anytime we pitch that nose up, even if we didn't add power, right? If we pitch the nose up, we might trade the kinetic energy for the potential energy. Um, think about slow flight, right? I think I said this in class, but if you're setting up for slow flight and you've been kind of monitoring the rest of the instruments and the parameters of those, and you've let some altitude escape you, right? So you're like 50 feet below where you need to be. Well, we know we have to slow down to probably mid 40s, low 50s, somewhere in there for slow flight, right? So if we are still at an airspeed of like 70 knots at that point, what we can do is we can add some back pressure, and what that does is it allows us to lose out on that airspeed we need to lose anyway. And we're trading that for altitude, right? So we can use that to climb ourselves back up to our starting altitude. Okay, so that's an example of transfer of kinetic energy to potential energy. And then if we have a lot of power, right? If we have leftover power, remember that's that rate at which work is being done. So if, let's say to, I don't know, move forward in level flight, we only need work to be done at a rate of, I don't know, 300, or not really 300, but let's say 50 horsepower, right? If we have an engine that's generating, let's say 100 horsepower at that moment, then we have 50 um, horsepower remaining, right? We can use that 50 extra horsepower to climb, right? We can gain potential energy or altitude by using that leftover energy. So, as I said at the beginning, right, the biggest thing we have to consider when we're thinking about a climb and how we need to manage our energy is what's our goal in the climb, right? What are we trying to do? Are we trying to gain the most altitude in the least amount of time or distance, right? So that's the thing that really kind of differentiates that. So if we are trying to, let's say, clear an obstacle, or we've got a short runway that we've got to get off of, then we will probably pitch for what's called best angle of climb, or the published V speed known as Vx, right? So that allows us the most altitude and the least amount of distance, okay? So we don't want to go that far while we're gaining that altitude, okay? So with this one, if we have a higher pitch attitude like this, right, we have to think about the direction that that propeller is now facing. Does that propeller still face forward, or I guess whatever the power plant is, because in the diagram here I've got some jets, right? So is that engine or propeller still facing forward to some degree? Yes, right? We still need it to face in that direction if we are to continue moving forward. If we don't move forward enough, we will not have enough airspeed to create lift, right? And we will stall. But we are using our excess thrust to move us up, right? So not only is this propeller or power plant facing forward, but you can see it's kind of in that diagonal direction. So yes, there is some being allocated to the forward direction, but there's also some of that thrust that's created by that power plant being allocated in an upward direction, right? So we're basically just using whatever's left of thrust to create that. And usually our VX airspeed that's published is somewhere below LD max, okay? And if we kind of put that in the context of the 172, forgive me, I'm not that great at 152 speeds because I didn't train in the 152. I didn't really fly it until I had to teach. But I believe it's like 54, I think, is what it is for VX. But anyway, 57 or 60 in the 172, right? That is below LD max, which we know is the same thing as VG, right? That's at 65, and there it is slightly below, right? We know it's 60 in the 152, and it's 54, so slightly below, okay? If we are trying to gain the most altitude in the least amount of time, then we would pitch for Vy, right, which is our best rate of climb, right? Keyword rate, because rate means work done in a certain amount of time, right? So if we have the best rate, that means that's the most work being done in the least amount of time, right? So work, right? That word, remember, we need excess power, right? Work is associated with power. So the faster the work is being done, the more power there is supplied. So where we took advantage of excess thrust for the VX climb, for the VY climb, we're now thinking about excess power, right? We want extra power, okay? So again, if we are using a certain number of horsepower or something to move ourselves forward, then now we are using the remainder of that power to move ourselves up, right? So that angle is not quite as high, okay? And it makes sense why we would do a VY climb on most days, right? Because we want the most amount of altitude that we can have in the shortest amount of time, so that in the event of an emergency, right, we've got that potential energy to use to help ourselves out. More potential energy means more time, right? If we pitch for that VG immediately, and we focus on just maintaining our energy and managing our energy, we will hopefully be more successful at having a safe landing, right? We have a better chance of making it back to the runway if we can have that immediate management, right, and more potential energy. So excess power, right? The more work is done, the faster the work is done, the faster the climb, or the more altitude we're able to gain in less time. And then if we are to continue exploring these two different V speeds, as we ascend in the atmosphere, your indicated airspeed might remain the same, but your actual airspeed, your true airspeed, is not quite the same because there's less air the higher we go. So Vx is going to increase over time, and Vy is going to decrease over time until they become one and the same. Once they become the same airspeed, we reach what's called the surface ceiling, which is an area where we can no longer climb at a rate greater than 100 feet per minute, right? And if you really tested that, you could get to the absolute ceiling, which is where the airplane just like won't climb at all anymore. Okay, so some notes on that. All right, let's talk about stalls. I've kind of talked about them throughout our examination of aerodynamics, but it's important to know that a stalled state results from exceeding the critical angle of attack. It doesn't really have anything to do with airspeed. We can stall the airplane at different airspeeds. Airspeed, remember, just controls whether we have structural integrity of the airplane after we stall, right? If we're too fast, wings are going to break off, other control surfaces are going to break into pieces. But if we're slow enough, then we can actually have the stall happen without substantial damage, right? Remaining below VA is what makes that happen. So the critical angle of attack is a fixed thing. It's different for every airplane, but it does not change at all. Okay, it's always the same. And when that angle of attack is increased, right, we can see that the airflow becomes more turbulent and airflow separation happens earlier and earlier. So view A, right, that air is attached to the wing for the most part, and that separation is happening somewhere further back, right? But view B, you can see it gets turbulent because it has separated earlier and earlier. And this makes sense due to the fact that the point of stagnation is changing. Right, so when we talked about the leading edge the first time, we've kind of generalized the fact that it usually is the place where air first encounters that wing, right? But the greater the angle of attack is, the less true that becomes, right? So if we have a pretty neutral angle of attack, yeah, this leading edge right here is going to be the place where that air hits the wing, right? And when it touches the wing like that, there is a point where the velocity reads near zero, right? That's the stagnation point. So the air just kind of hangs out there, and then air splits up around that and goes on either side, right? If we think about kind of that friction with the surface that we talked about when we examined skin friction drag, it's kind of the same thing there, right? So there's some air that attaches to that surface because it's hitting it dead on, and the friction is too great to detach it from that surface. Okay, so air moves around the wing in either direction, and as we increase the angle of attack, that stagnation point is no longer at the leading edge, right? In this view, the leading edge is here, but you can see, right, the first point that is exposed to the airflow is like somewhere down here. Okay, so if that stagnation point is lower, then you can imagine, right, that that distance that that air has to travel to go around the upper portion of the wing has increased greatly, right? It hasn't really increased for the bottom. In fact, you could say it has decreased, right? So it doesn't really need as much energy to go around there, and that's fine, right? But if we don't have enough energy for that air to go around that lengthened path of travel, then it's going to separate sooner, right? Coanda effect can only keep that air attached to the surface to some degree, right? There's always limits to everything. So separation happens earlier and earlier as that angle of attack increases because that stagnation point moves further down on the underside of the wing. And we eventually get to the point where there's just not enough airflow attaching to that upper surface, right? That center of lift or center of pressure has moved up and it can't really move up anymore. So that wing can no longer generate sufficient lift once that angle of attack is exceeded and a stall happens. Now, be careful because a stall does not mean that the airplane is no longer producing lift, right? It is still producing lift. There is still some interaction of that air with the surfaces, but it's just not enough to create sufficient lift. So that's why you have loss of altitude that happens. It's not like we just plunge out of the sky because we have no lift, right? We do fall a little bit because we just don't have enough lift. So stalls are some of the first things that you guys learn, right? As new pilots and everything, we need you guys to understand what that stalled state looks like and how to deal with stalls in case you encounter one, right, in real life. So we familiarize you guys with the behavior of the airplane, right? So you might have some buffeting. The control surfaces are going to feel mushy. And all that means is that if we've slowed down, right, then the control surfaces aren't going to be as effective as they once were. So you need more back pressure, ailerons, or rudder to do the same thing to the airplane as you were doing before. So that's going to happen, right? You're going to have stall warning horn come on as you get closer to that stalled state, and you're going to have decreased airflow. right? And you can hear that. You can hear that there's less air traveling over, it gets quieter. And you have all these cues in place that just communicate to you that you are near that stalled state. So we can use this, right, to anticipate that, right? If we weren't training to do stalls, if we were doing something that got us close to a stall, we've got all of these devices and indications that tell us that we are getting close to that stalled state. That way we can go ahead and do what we need to do to avoid the stall, which is not increasing our airspeed or anything like that. It is mainly getting that nose down, right? So that we can um, go below that critical angle of attack. So we don't exceed it. If we go beyond it, we will stall, right? It has nothing to do with airspeed. It just so happens that most of the time we do have stalls. It's because we've decreased the airspeed and we are trying to increase the angle of attack beyond its limits to make up for that loss of airspeed. Okay. So stalls are kind of scary at the beginning, right? But if you know what to do, they're not so bad. Spins are another matter. Spins are still stalls. They're just aggravated stalls. Okay. And when we have a spin happen, what's going on is that one wing is more stalled than the other. Mainly that's due to lack of coordination. So if we don't have enough rudder to counter those turning tendencies, we will have lack of coordination and possibly a spin on our hands. So there are four stages to the spin. Okay, the first is the entry, and this is where we're just supplying that aircraft with all the ingredients it needs to spin. So we have the angle of attack getting close to that critical angle of attack. So we've got that stall ingredient in place, and then we just don't have enough coordination, most likely, and that puts us in a slipping condition, right? If we don't have enough rudder for the rate of turn, so we slip, and then once we have those things, we've got those ingredients created, right? Once that happens, right, we go into the spin, and the rotation begins to happen in the direction of the more stalled wing. That's what we call the incipient phase, right? So the rotation rate has not quite stabilized yet. It's just beginning to happen, and that nose is dropping down, right? Because we don't have enough lift to maintain level flight. Once we've had that happen, once the rate of rotation kind of stabilizes and there's no more acceleration in any manner, then we are in the developed stage, right? So everything is stable, and then recovery is the last part of that. So recovery we kind of list as a separate stage because it is, but hopefully we are looking to put the recovery between the incipient and developed stages if we were to actually get into a spin. A spin is a little harder to recover from if we wait until the developed stage to put in those items and everything. It's not impossible, but it is a little bit harder. So the earlier we can exit the spin, the better. The recovery includes the PAIR acronym, right? So power goes idle, ailerons neutral, rudder in the opposite direction of rotation, and then elevator forward pressure to break the stall, and then elevator back pressure to pull ourselves out of the dive. Now, a couple things for all of these items. We have to kind of understand why they are the way they are and how to do them. So power idle, why do we not want to have any power? Well, if we are in a state where the airplane wings are not creating enough lift to keep us sustained in level flight and we're falling towards the ground, we don't want to meet that ground any quicker, right? So we can decrease that power all the way back to idle to not encourage that propeller to help us out, right? This is an instance where that thrust is now acting in a downward direction if we keep that power in. And we know that downward forces, right, complement one another. So we have gravity, or I guess weight, acting downward towards the center of the Earth. If we leave power in, we now have thrust acting downward towards the center of the Earth along with it. And we already don't have enough lift, right, to counter that. So I guess we're going to have a hard time being able to pull ourselves out of that dive, right? We know that the aircraft, again, has structure limits due to things like load factor. Okay, so we want that power idle as soon as possible. We don't want any extra airspeed on the way down. Ailerons neutral, that one kind of throws people for a loop because you would think if the airplane is rotating in a certain direction, then we would have ailerons in the opposite direction, right? Because it seems like it is a rolling motion, right? And I mean, yes, I can understand why that is the thought process, but it's not quite the right way to go about it, right? Remember, the aggravated stall happened as a result of lack of coordination. So it's really that lack of rudder or a problem with yaw that kind of makes that happen, right? That airplane enters that auto rotation in the spin as a result of that. So that's the fix for it, okay? Now, ailerons, let's back it up. Let's say that we don't see how logical ailerons neutral is. So the first thing we would probably think about is, well, if let's say we're in a spin to the left where we have leftward rotation, then the fix would logically be to add aileron to the right, like the controls to the right. So turn them in the opposite direction. Well, if we think about why we are rotating to the left, then it becomes quite clear actually, right? So if we're rotating to the left, that means that we have the left wing more stalled than the right wing, okay? If we turn our controls to the right, then what are we doing with those ailerons, right? Thumbs up, ailerons up, so that right aileron goes up, the left one goes down. But what is a stalled state, right? It is any time that critical angle of attack is exceeded, right? So on that left side, if we are lowering that aileron, we are in effect increasing that angle of attack, increasing that stalled state of that already more stalled wing and making it harder to recover, right? It's not going to want to exit that state if you're making it worse, right? So you are increasing the disparity between the wings and depending on where you are in the spin, right, you could possibly make it worse. You could increase that rate of rotation, maybe leading to some structural damage or something of that nature. So you don't want opposite ailerons. So if that's the thought process and we don't want one wing to be more stalled than the other, then you might think, okay, well, let's go controls in the direction of rotation because then that would equalize the stalled state. And yes, that is what would happen, right? If we increase the angle of attack on the right wing to match that of the stalled state on the left wing, then yes, we would equal that out. However, if we do not recover from that stall, right? Again, both those surfaces are not adding enough, I'm sorry, they're not providing enough lift, right? And the whole cause of the spin was the fact that we were uncoordinated, right? We didn't have enough rudder, so that's why we're spinning to the left, right? The direction of the more stalled wing. So if we equalize how stalled they are without breaking the stall, then what you're going to have left over is just you're still going to have rotation, but it's going to be around that vertical axis. Um, in a yawing motion fashion. So you will basically go from a nosedive spin to a flat spin. So your nose is going to come up, right? You're going to be at kind of a neutral pitch attitude, but you will still continue yawing in the direction of rotation, right? Because it was a rudder problem initially, lack of coordination. So if you have a flat spin happening, those are very hard to recover from because when you are spinning flatly like that, you don't really have that airflow interacting against the wings in the way that you would need them to create that lift, right? If you are in a nosedive, at least you've got that airflow acting on the leading edge of the wing and going, interacting with the whole entire wing so that you can produce some lift out of that and come out of that, right? But if you've got a flat spin going on, you are literally just helicoptering down to the ground and you've got the airflow basically just interacting with the bottom of the wing, right? So you don't really have that attachment of the airflow to the wing anymore. And it's very, very hard to recover from that, right? Your control surfaces aren't as effective because the air is not moving over them in the same way. So it's hard to get that nose back down to generate that airspeed to recover. Okay, so don't go ailerons in the direction of rotation either, right? There's no good way for the ailerons to go because both of them are bad, right? So that's why we leave ailerons neutral. And then that discussion about ailerons kind of talked about why we have rudder in the opposite direction of rotation, right? It was a lack of coordination problem that caused that auto rotation. And the only reason that nose is down, right, for the nosedive is because that nose is heavy, right? If it wasn't heavy, if the aircraft was kind of equally light, we would probably already be in a flat spin. But again, the aircraft, if you respect the limits of the center of gravity, should have that nose down tendency, and that's what happens as a result. That's also why in aircraft that are approved for spin training, and aerobatics and things like that, you need to have that CG in the utility category, right? The utility category, rather than the normal category, is a more forward CG that basically just bolsters that tendency of the airplane to nose down so that you don't get yourself into a flat spin, okay? So that is why we need rudder in the opposite direction of rotation, and then elevator forward to break the stall, right? That's always how we break the stall, and then back to recover. When we are using the elevator in the forward motion, so we're pushing forward, um, sometimes you have to do that along with the rudder in the opposite direction to make sure that we have enough airflow over that control surface for it to work properly. If we don't break the stall and increase that airflow, the rudder's not going to work as well. So those things we kind of have to do in tandem together. Um, and then when we are pulling ourselves out of that dive, once we have that rotation stopped, we have to be extra careful to not pull too hard, right? Because as we descend, right, as we're pulling back to pull out of that dive, we're increasing the load factor on the airplane. And remember, it serves as that multiplier, right? So if we have a load factor of like 2, then that doubles the weight of the aircraft. So if we just yank back, right, we probably won't have any wings anymore. So we probably shouldn't do that, right? So slowly add that back pressure to kind of ease yourself out of the dive. Okay. And again, the earlier the recovery can be, the better, right? Because if you're already hurtling towards the ground, that's not going to help with keeping that airspeed on the low side as you try to pull out. Again, if you're finding yourself going above VA, be extremely careful, right? No abrupt movements. This is also why when we do spins, we make sure that we are high enough, right? Like 6,000 AGL. Okay, if we're low and we're panicking because the ground is coming up soon, we're not going to want to slowly ease ourselves out of the dive, right? We're going to want to yank on those controls and damage the aircraft. So make sure you're high enough. Spins, you can lose about 1,000 feet of altitude per rotation, right? Once you're developed and everything. So it's no joke, right? Make sure you are high enough if you are ever doing spin training. Never just try spin training alone. I would say always go with somebody, right? If you're curious about it, ask a flight instructor, right? Somebody who specializes in spin training to go with you. And if you choose to do CFI, you will likely have to do the spin training, right? So you can get your spin endorsement. Otherwise, you have to, I believe, demonstrate proficiency in spin recovery on the check ride, and I don't think anybody wants to do that. So as long as it's intentional and done safely, right, recovery shouldn't be a problem as long as you implement the correct steps, right? But when we are out flying altogether, this is something we just don't want to deal with because if we're out training, working on stalls, and we don't have enough coordination, well, we're not going to have those 6,000 feet to recover, right? And it might take us some time to recover, right? Sometimes, if people are in a panic state about spins, they will grab the controls and move them in a way that is detrimental to the recovery process, right? So part of our job as flight instructors is sometimes having to get people to let go of the controls. We have to kind of fight them for the controls, and that takes time. And by the time we're done with that, right, we're too close to the ground, our airspeed is too high, so it just becomes disaster after that. So really, really make sure that you're maintaining that coordination. Okay. All right. The last thing we have to talk about on a lighter note is just forces and descents, right? So if we just, let's say we want to descend and we just push the nose forward, we leave the power where it is, we're likely not going to have a steady descent. What might happen is we might descend a little bit, but because our airspeed is going to increase, because we've maintained that power setting and now it's helping, right? Remember, it's acting in the same direction to a part as weight. You will have an increase in airspeed, and when we have more airspeed, that's more air acting over the control surfaces, causing that elevator to move the tail down and that nose to go back up. So we would climb. Okay, and eventually, if we follow that thought process, we would essentially go back to our original condition at the altitude we started at if we had a stable aircraft. But if we want to descend, right, we know we have to reduce the power a little bit. And what that does is it allows us to change or decrease our angle of attack without increasing our airspeed so much, right? Um, so that we can initiate that descent. So if we are maintaining our airspeed but decreasing our angle of attack, or even slowing down, right? We lose out on that vertical, I'm sorry, the just lift altogether, right? So if we don't have as much lift as we had before, weight has not changed, and now that weight is acting or is stronger than lift in that moment, right? Once we kind of establish ourselves on a flight path and a descent, right, then they are kind of equalized again. But when we are initiating that descent, we have to decrease lift so that it's not as strong as weight. Um, Something cool to think about is the angle of attack, right? When we're descending, we still have an angle of attack depending on our rate of descent that's kind of like our angle of attack that we would have in cruise at a normal airspeed, right? So if we are descending, right, and we are decreasing our pitch attitude to decrease our or to change our chord line, right, we might go from this to this, right? It might be straight, okay? But our flight path when we were in straight and level, which is what this upper drawing is, was like this, right? So that's our angle of attack. But now because we've changed our flight path in the descent, right? Maybe like this, right? Depending on how steep our descent is. So in essence, right, our angle of attack has stayed the same. There was a moment where it was smaller, right? Because there is a transition moment between these two pictures where our chord line and flight path are pretty much equal. And then once we are actually descending, right, then the um, flight path drops down, right, where the chord line stays the same. So they essentially have the same angle um, even when you are descending, right? So people forget about that. People think that you have to have a positive angle of attack all the time just to stall, right? Or an extremely high angle of attack, um, I guess pitch attitude to stall, right? And you don't necessarily have to have that. If you've got a descent rate like this lower picture that I've drawn here, then it doesn't take much to exceed the critical angle of attack, right? You could raise that nose and pitch a few extra degrees until you exceed that critical angle of attack. But here in straight and level flight, right, we would have to increase that angle of attack greatly, but it still doesn't change the fact, or pitch attitude greatly, right, to exceed the critical angle of attack. But it doesn't change the fact that the critical angle of attack has been exceeded, right? That is what a stalled state is. So don't think that you have to have a super high pitch attitude when you're descending to stall the airplane, because you don't, right? And that's why we are so much more guarded in terms of airspeed management and energy management when we are descending, especially when we're close to the ground, because we know A, that it doesn't take a lot for that wing to stall, right, the aircraft to stall, and then two, we have less time to recover. All the scenarios we use, right, the power on, the power off stall, yes, we are simulating that either takeoff stall or approach to landing stall, right? But we, we have that area below us for recovery, right? We make sure to do these things at least 1500 AGL per the ACS and our safety, right? We might even increase that if we feel that it might take us a little extra time to recover. So when we're close to the ground like that, we're a little bit more careful about those things because it can kind of sneak up on you, right? It doesn't feel like you're pitching that high up, and you're not, right? For the aircraft to stall, and then there's less time for recovery. It's even worse if we're on that short runway and we're on the north side, right? Or even the long runway too. We've got trees before that, so we really don't want to hit those if we're stalling. So we want to guard ourselves from that. And then if we're on the south side, you've got the power lines against the road and the taller ones in the junkyard if you're using the long runway. So obstacle clearance is something that we have to also be careful of. Okay. So I know you guys can't ask me questions now because I'm recording this, but if you have any at any point, let me know. I hope that this video lecture is insightful. You can go back and view it at your discretion to make sure that you understand the principles. And if I explained anything in a weird way, sometimes I struggle with words, just let me know, and I'll try my best to kind of clear that up. But hopefully this is helpful.